both the example, we are supposed to calculate either the maximum value or the minimum value. So nearest means is nothing but minimum value. F of C is called as maximum value and C is called as the point of maximum value of f in I. dy by dx is nothing but the slope of the tangent which is parallel to the x-axis, and there it is 0. Decreasing means we usually say negative. Increasing means positive. So that is why here less than 0 and greater than is 0. Hello everyone, a warm welcome to one and all. This is your Shruti ma'am lecturing in Vidhyaashram, the Temple of Excellence, Mysuru. So we are in the chapter Application of Derivative. In this section, we are going to learn very important concept. So with the help of finding the derivatives of a function, we can find the maximum and minimum value of the function, which is termed as maxima and minima. So here, by finding the derivative, how we can able to find out the maximum value or minimum value of a given function. So first, the concept of derivatives are used to calculate the maximum or minimum value of various functions. How? We will study it later. In fact, here by finding the derivative or by finding the maximum value or minimum value of a given function, we can able to identify the turning points in the graph. That is, if a graph of sin x will be like this. So like this it move on. So we can see this is the maximum point and this is the minimum point. So it helps us to identify, or by plotting the point, we can easily draw the graph of a given function given. So just by plotting the points, by finding the maximum and minimum values of a given function, we are able to sketch the graph required for the given function. So this helps us to find out or to analyze how the function is defined in the given interval or given domain. So now, let us take an examples of our in a daily life. So the very first example here is taken. The profit from a grove of orange trees is given by P of x is equal to ax plus bx square, where a and b are constant and x is the number of orange trees per acre. How many trees per acre will maximize the profit? So if some x number of orange trees are planted in 1 acre, then what is that number of trees or orange trees which is given in the form of a function, that is P of x is equal to ax plus bx square, where x represents the number of orange trees, a and b are constant. Then what kind of number of orange trees have to be planted in an acre with the following function so that we will get the maximum profit? This is the question. And second question says that an helicopter of enemy is flying along the path given by f of x is equal to x square plus 7. So the helicopter is moving along the curve x square plus 7. A soldier is placed at the point 1, 2, wants to shoot the helicopter when it is nearest to him. What is the nearest distance? An helicopter is moving in a curve, circular or some curve in a path, and a soldier is at the point 1, 2. That is, graphically we represented a soldier is sitting at some place where the coordinates are given in the point of 1, 2. Now he has to shoot the helicopter when it is almost nearest to him. So how to find out the nearest distance so that he can shoot the helicopter? So in both the examples here, in both the example, we are supposed to calculate either the maximum value or the minimum value. So nearest means is nothing but minimum value. So, and both the functions are expressed in terms of a quadratic equation here. By solving the given function, we are supposed to calculate the maximum or minimum value for the given condition. So this is how we are going to calculate the maximum and minimum values of a given function. So from the previous example, thus we can define a function which is maximum or minimum in the following definition form. Let f be a function defined on an interval I. So this is on an interval I. Then f is said to have maximum value in I if there exists a point C such that f of C is greater than f of x. Suppose this is a function or this is some curve here. This will be the point C and these are all any x. Any x belongs to C. If there exists a point C such that f of C, the functional value at C must be greater than other values of f of x for all x belongs to I, and C must also belongs to the same interval. Then f of C is called as maximum value and C is called as the point of maximum value of f in I. So whatever the value at this point, so if this is your x and y axis here, this denotes the point C and this is your f of C. So therefore here C is called as the point of maximum value and f of C gives you the maximum value. The condition is f of C must be greater than any other values of x in the interval. Next, f is said to have a minimum value if there exists a point C such that f of C is the minimum value when compared to other values of x belongs to the interval. Then we say f of C is the minimum value and C is called as point of minimum value. Other than that, we may arise at some kind of points where it is neither a maximum nor a minimum value, and that is called as an extreme value. So what is this is extreme value? F is said to have extreme value if there exists a point C in the interval such that f of C is neither maximum nor a minimum value for the given f of x. So in that case, the value is called as extreme value and point C is called as extreme point. So here f of C is called as extreme value and point C is called as extreme point. So here I have taken three graphs. So based on the definition stated above, we can see here. So here f of C, this is our f of C. So this is the maximum value and behind this or after this, so or left towards the C or right towards the C, you can see the functional value is less than f of C. So here also f of C is greater than f of x and here also you can see f of C is greater than f of x. So thus this points will be the maximum value and C is called as point of maximum value. And here also you can clearly say the function is a straight line. So this is the minimum value and this is the maximum value according to the graph here. And here also you can see here functional value of C is minimum and this is called as minimum value. So the point, so this is f of C is the minimum value and C is called as point of minimum value. So thus by the definition stated above, we can look at the graph and analyze what will be the maximum value and minimum value of a given function. So first question here is, find the maximum and minimum values, if any, of the following function f given by f of x is equal to x square. So clearly f of x is equal to x square is a parabola. We have known that. So we can see here. So let me plot a function 0, 1, 2, 3 like this. And here, so here 1, 2, 3. Let me plot here in the form of 2, 4, 6, 8, 10, etc. So let me take this as y, y dash, x, x dash. So clearly, let us substitute the value. For 0, it is 0. For 1, it is 1 somewhere here. For -1 also, it is -1. For 2, it will be 4. And for -2 also, -1, -2, -3 also, it is 4. For 3, it is 9 somewhere here. And for -3 also, it is 9 somewhere here. So here I have plotted the points here. So let me sketch a graph here. So this is how we will get the graph. So this is the parabola. It has to touch the axis here. For 1 also, I will get 1 since I cannot include it. And for all the other points, it is a straight line passing through the origin. So this is the graph now. Now here, I know that 0 will be the minimum value, but I cannot write 0 as the minimum value. Since it is an open interval, I have to take the values between 0 to 1. But here we can clearly say the minimum value is very close to 0. But I cannot write exact value for the minimum value or exact point of minimum value. I cannot exactly write what is the point of minimum value and what is the minimum value. Here also we can see this is the very close to 1 and it will be the maximum value. We can know that it is very close to 1, but we cannot write the exact value. And thus here also the maximum or minimum value cannot be defined. Thus we say that this function does not have any maximum or minimum value, or we can say it has neither maximum or nor minimum value. Suppose if the same function is given with a closed interval, that is 0, 1. How will be my graph? My graph will be like this. So if this is 0, this is 1. So this is my graph. So these are the points now. Now I can say f of 0 is equal to 0 is minimum value and f of 1 is equal to 1 is the maximum value. Since I can include it and I can exactly write the point of minima and point of maxima as well as what is its minimum value and what is its maximum value. So this is the maximum value I'll get whenever the interval is defined. But here it cannot be defined. So therefore, this function has neither maxima nor minimum value in the interval 0, 1. So thus we can say that whenever the interval is closed, we can clearly define the maximum or minimum value. When it is open, we cannot identify the maximum or minimum value for this function. Next we have local maxima and local minima. So let us take an example of a graph here. So here you can see the graph is decreasing and increasing, decreasing, increasing, decreasing. And here we have 4 points. I have plotted A, B, C, D here. So you can clearly say at point A, so here the value of the function is minima. At the point B it is maxima. And here also it is minimum and here it is D. So at some neighborhood of point B or point D, we can identify the function is increasing or the function has the maximum value. Thus we can say B and D as local maximum value and B, D can be called as local maxima. And here you can clearly say at some neighborhood of A here and at some neighborhood of C here, the function is decreasing and it is almost minimum. And thus these values can be called as local minimum value and these points can also called as local minima. So from the observed graph, so we can define a definition that let f be a real valued function and let c be an interior point in the domain of f. Then c is called as point of local maxima if there exists h greater than 0 such that f of c is greater than f of x for all x in c minus h, c plus h. Next, the value f of c is called as local maximum value. Similarly, c is said to be point of local minima if f of c is less than or equal to f of x for all c minus h, c plus h, and f of c is called as local minimum value. So here, let's see the definition with this graph here. So this is our f of c here. So this point is f of c here. So I said h exists and this side we can call it as c minus h and this side we can call it as c plus h. So thus the interval c minus h, c plus h. So this is the interval c minus h to c plus h. Similarly, you can observe. So this is the interval from c minus h to c plus h. H is a value which is less than c and when you subtract you will get the curve this side and c plus h means you will get the curve this side. So according to the definition, previous definition, there exists h greater than 0 such that f of x is greater than f of x in the interval. So you can clearly say from the interval, so this is the point h if you say that. So from the interval c minus h to h, the function is increasing and then it decreases. So thus f dash of x is greater than 0 and f dash of c obviously will be 0 because at this point f is differentiable and dy by dx is nothing but the slope of the tangent which is parallel to the x-axis and there it is 0. So dy by dx is 0 whenever the tangent or the slope of the tangent is parallel to x-axis. And then here you can see the function is decreasing from the interval h comma c plus h. So thus, observing this graph, we can say this is the maximum value or local maximum value. And here also you can clearly say first from the interval c minus h to c. C you have to take here c minus h to c. Clearly you can say here the function first decreases and then increases to c plus h. So this is the interval. From c to c plus h, function is increasing. From c minus h to c, the function is decreasing. Thus, whenever the function decreases and then increases, that is decreasing means we usually say negative, increasing means positive. So that is why here less than 0 and greater than is 0. So the function must change its sign from positive to negative. It goes on. Then you have a local maximum value and from negative to positive it goes on. So that is first it decreases and then it increases. Then you will have a local minimum value as well as local minima. Thus by observing these graphs, we can give a definition that let f be a function defined in an open interval I such that c belongs to I. C belongs to I and f has local maxima or local minima at x is equal to c, then either f dash of c is equal to 0 or f is not differentiable at c. That is, at this point, f dash of c must be 0 for all c belongs to the interval of the domain of f. And in this case, f dash of c must be 0 or f is not differentiable at that point. That is, if f dash of c is equal to 0, then c must be either local maxima or local minima. So this is the statement of this theorem. But there exist somewhere cases where f is 0. That is, the value of the function becomes 0, but that value cannot be taken as local maxima or minima. So then take an example for that. So here I have taken an example of x cube curve. So the theorem states that if f dash of c is 0, then c must be local maxima or local minima. But this is not true for all cases. So here you can see the converse of the above theorem need not be true. That is, a point at which the derivative vanishes need not be point of local maxima or local minima. It is not always point of local maxima or local minima where the derivative becomes 0. So I have taken f of x is equal to x cube, then f dash of x is 3x square. At x is equal to 0, you can clearly see that f dash of x becomes 0. But 0 is neither point of local maxima. So to become a point of local maxima or local minima, the function must be increasing to decreasing or decreasing to increasing. That is, it must change its sign here. So but here, so it is just an increasing function clearly. So it doesn't change its sign. Thus, we call this point as point of inflection. It is not minima or maxima or a local minima or local maxima. It is just a point of inflection. So there exists a point of inflection where the derivative can become 0. And the derivatives are 0 even at the point of local maxima or local minima. So next is critical point. What is this critical point? A point C in the domain of the function where f dash of c is 0 or f is not differentiable is called as critical point. Next, note that if f is a continuous function at c, f dash of c is equal to 0, then there exists h greater than 0 such that f is differentiable in the interval c minus h comma c plus h. So if you take a curve like this, so if this is your c, the interval c minus h to c plus h. Even though f dash of c is equal to 0 here or f is not differentiable at this point, but there exists an interval from C minus H to C plus H where f is differentiable. Observing the following results, we get a theorem called the first derivative test. What does this first derivative test says? That is, let f be a function defined on an open interval I. Let f be continuous at the critical point C in I. So, at the critical point, the function must be continuous. Then, f dash of x changes sign from positive to negative. That is, first it increases and then it decreases. That is, f dash of x is greater than 0 for a point sufficiently close to the left of C, and f dash of x is less than 0 at a point sufficiently close to the right of C. That is, I have taken an example of this curve. So, here you can see here. So, this is the point C, and towards point C the function is continuous, and here you can see f dash of x goes on increasing, and here f dash of C is 0, and here it decreases. It is less than 0. So, this is positive and negative. So, when it changes from positive to negative and f dash of x is greater than 0 towards left of C, and it decreases towards right of C. Towards right of C, the function must decrease. Then we call it as point of local maxima. So, thus we call point C as point of local maxima. The same definition applies for the point of local minima. That is, f dash of x changes from negative to positive. So, here f dash of x is less than 0, and if this is your point C here f dash of C is 0, and here f dash of x is greater than 0. Thus, it decreases and then increases. Thus, it changes sign from negative to positive, and towards the left it is less than 0, towards the right it is greater than 0, and thus we call it as a point of local minima. And there exists f dash of x which does not changes its sign as it increases or decreases through C, and it is neither a local maxima nor a local minima, then it is called as point of inflection. So, we have taken an example of x is equal to x cube here. Here the function goes like this. So, this point is called as point of inflection because here the curve never changes its sign. That is, it is neither a point of local maxima or a point of local minima, and that point is called as point of inflection. So, here I have taken an example of a graph here. So, you can clearly see here, if this is C1, towards left it is positive, towards right it is negative, and this point is where f dash of C1 is 0 is called as point of local maxima. And if you take this curve here, towards this curve, towards the left it is decreasing and towards the right it is increasing, and thus we arrive at the point where f dash of C2 is 0. This point is called as local minima. And for this curve also, increasing then decreasing, this is a point of where it is a local maxima, or we call it as a point of non-differentiability also. It must not be differentiable at that point. Similarly, this is a point of local minima, or we can call it as point of non-differentiability. So, next question we have here, find all points of local maxima and local minima of the function f given by f of x is equal to x cube minus 3x plus 3. We have studied first derivative test. So, let us apply the first derivative test for this question. So, we have f of x is equal to x cube minus 3x plus 3. So, let us find out the derivative. F dash of x cube is 3x square minus 3 here. If you take 3 as a common factor, it is x square minus 1. So, we can write it as 3 into x minus 1, x plus 1. So, thus here, if you put f dash of x is equal to 0, this implies x is equal to 1 and x is equal to minus 1. Now, we got the point as x is equal to 1 and x is equal to minus 1. So, therefore, x is equal to plus or minus 1 or the critical points. Now, let us take the point here And let's study the sign of f dash of x. So if you take here 1 and close to right towards right. So when you go close to right towards 1, here the sign of f dash of x, here if you take exactly 1 also, here it is 0. So if you take close to 1, that will be greater than 1, then clearly f dash of x is greater than 0. If you take close to left, take like 0.9999. So if you take 0.999 something, the value will be obviously less than 0. So here, according to this, if you take the point 1 close to right, it is greater than 0, then the curve will be like this. So close to the, if this is the point 1, close to right it is greater than 0 and close to left it is less than 0. This means 1 is the point of minima, that is 1 is the local minima, and the value will be, that is 1 is point of local minima. And what will be f of 1? So f of x is x cube minus 3x plus 3. F of 1 will be 1 minus 3 plus 3, which is 1, is the minimum value. Now let's study the point close to minus 1. So what happens when it is close to right and close to left? So the function or f dash of x is 3 into x minus 1 x plus 1. So if this is your minus 1, this is the point minus 1. When you go close towards right, that is after minus 1, you can take that is minus 0.999 something or 0, 1 like that. So towards right, the function is negative. The function is negative. That is f dash of x is less than 0. Similarly, when you go close to the left, from the left you go close to the left. So here f dash of x is greater than 0. So thus we can say minus 1 is point of local maxima. So this implies f of minus 1 if you take. So the function is x cube minus 3x plus 1. So it becomes minus 1 plus 3 plus 3, which is equal to 5. So 5 will be the maximum value and point of maxima is minus 1 and 1 will be the minimum value and point of local minima is 1. So next question we have, find all points of local maxima and local minima of the function f given by f of x is equal to 2x cube minus 6x square plus 6x plus 5. So let's take f dash of x. F dash of x becomes 3 2s are 6x square minus 12x plus 6. So if you take 6 as a common factor, it is x square minus 2x plus 1 and f dash of x is 6 into x minus 1 whole square. So clearly you see x minus 1 whole square is a positive quantity and 6 is a positive quantity. Thus it is greater than 0. That means f dash of x will be in the form of like this. It is a curve. So for a negative value or positive value or very close to, for any point close to right or close from left, the value of the function is only positive. That is f dash of x never changes its sign. So since it never changes its sign, if you put f dash of x is equal to 0 here, f dash of x is equal to 0 implies we get here x is equal to 1. So for any point to be a critical point, so critical point means it is neither a local maxima or local minima. So thus to be a critical point, either the function has to change from positive to negative, that is increasing to decreasing, or decreasing to increasing, that is negative to positive. But here for all the values of x, or for x is equal to 1 also, the function is only positive. It is never changing its sign. So it is neither increasing to decreasing or decreasing to increasing. So therefore, x is equal to 1 is neither a point of local maxima nor a point of local minima. So if it is neither a point of local maxima nor a point of local minima, this implies x is equal to 1 is a point of inflection. Because the function has never changed its sign, and hence we call it as a point of inflection. So in this session, we have learned what do you mean by local maxima, minima, as well as the first derivative test for the functions given. So we'll meet you in the next session with few more concepts of maxima and minima. Until then, keep watching, keep learning, keep exploring. Thank you.